So in question number 18 here, asked to find the first derivative for each of the following functions, and we're just using the derivative rules. We're not into the definition of the derivative anymore. So power rule. So the 7 comes down and multiplies by the 4 to give you 28. Reduce the exponent by 1 to 6. The root 2 x cubed, so the 3 comes down in front. 3 times the root of 2 is just 3 root 2. Reduce the exponent by 1 to 2. And derivative negative 8x is negative 8. Remember, this is really x to the first. So when the 1 comes down and multiplies by negative 8, that's negative 8. And then when you have a power of 1 here and subtract 1, it's x to the 0, which is equal to 1. So that's why there's no x's anymore. The 6 is a constant, so its derivative would be 0. That's the whole derivative. Now for f here, this is actually chain rule because we have a power function. Okay, so we're going to use some power rule here, but there's not just an x in here. There's a 2x cubed minus 5x. So we'd start by differentiating the outside function, which is the power of 6. So we're going to use the power rule. So the 6 comes down in front, and then it's the original function inside, and then reduce the exponent by 1. So 6 minus 5 is 1. And then you multiply that by the derivative of what's in here, and that's what's going to be in the second set of brackets here. So the derivative of 2x cubed would be 6x squared. 3 times 2 is 6. Reduce the exponent by 1 to 2. And the derivative of negative 5x is negative 5. Now, I would normally write this in the front here along with the 6. If you want to expand the 6 in, I suppose you could, but otherwise I'll just leave it in a factored form like this. Now, this is a quotient, but that 7x divides evenly into all these terms. So the quotient rule would work here, but to divide the 7x first will make this simpler. So 7x goes into 28x cubed, 4x squared times. 14 divided by 7 is 2, x squared divided by x is x, and negative 21x divided by 7x is negative 3. So now just power rule on each of these parts, or this is actually the derivative of constant 0 actually. So the derivative of 4x squared would be 8x, derivative of 2x is 2, so that's the whole derivative. For D here, there's actually a couple different differentiation rules here. We have a product, so this 7x to the 5th and the root of 3x to the 4th minus 5x squared is a product, so we use product rule here. But when you get into differentiating this, it's very similar to this one right here because it's a power of a function of x. So writing that as the power of a half first, the root, I'm going to start with product rule. So the derivative of 7x to the 5th would be 35x to the 4th, just using power rule. So derivative of the first function times the second, and then plus, and now it's going to be the first function, the 7x to the 5th, times the derivative of this function right here. So the half comes down in front, that's that 1/2 there. Original function's inside to the power of, and we subtract 1 from a half, you get negative a half. And then you multiply it by the derivative of what's in here. Well, 3x to the 4th, the 4 comes down and times 3 is 12, and reduce the exponent by 1 to 3, and derivative of negative 5x squared is 10x. So that's all the differentiation done. Next, I'm going to do some simplifying to write this in a considerably simpler form than this. If you look at my final answer here, it's a lot simpler. So the first thing I do is rewrite this as the power of a half. And then over here, this is the power of a half, but it's a negative a half, so I'll write that in the bottom. Okay, the half here will multiply evenly in, or divide, the 2 will divide evenly into both of these. So we would get a 6x cubed minus 5x. And if you multiply the 7x to the 5th in by those, 7x to the 5th by 6x cubed is 42x to the 8. And 7x to the 5th times the negative 5x would be negative 35x to the 6. So that's where that comes in the numerator. Now, notice that this is my denominator here. It's actually the same. This is exactly the same root here. So if I were to, so the common denominator would actually be this. See, right now this is over 1. So I'm going to multiply this one by the root of 3x to the 4th minus 5x squared top and bottom, and I will have a common denominator. This will, as you can see, make this quite a bit simpler in the end. So if you multiply the root of 3x to the 4th minus 5x squared by the same thing, well, you get what's underneath the root. So basically it's 35x to the 4th times that. So if you multiply the 35x to the 4th by both of these, this is what you get. plus this. Now, they're both over the same denominator, so I could have written it over one denominator, and then we collect like terms. 105x to the 8th plus 42x to the 8th is 147x to the 8th, and negative 175x to 6 plus, or minus actually, minus 35x to 6 is negative 210x to 6. And so that's the simplest way to write that. E is just, we could use quotient rule here, but you can do this a little simpler because there's a constant in the numerator. You could actually bring this 5x squared plus 8 up, or cubed up, and it would be to the power of negative 3. So we can actually just use chain rule then. So the negative 3 comes down and multiplies by the 5 in the front to give the negative 15. Original function inside. And then we subtract 1 from the exponent. Negative 3 minus 1 is negative 4. And then you multiply that by the derivative of what's in here. So that would be 10x. So 10x times negative 15x, or negative 15, sorry, is negative 150. And then we would write this as 5x squared plus 8 to the power of 4 in the denominator. For f, we're differentiating sine of x squared plus 1. So derivative of sine is cosine. Cosine, original function, times, again, chain rule, because it's not just an x in here, it's x squared plus 1. And so the derivative of x squared plus 1 would be 2x. I will normally write the 2x out in front of the cos. So somebody doesn't think, well, let's multiply by the x squared plus 1, because it's not supposed to be. So 2x cos x squared plus 1. For g, the derivative of 4e to the x cubed is the original function, times the derivative of the exponent, again, chain rule. So the derivative of x cubed is 3x squared. I would normally multiply that by the 4 to write it as 12x squared, and then e to the x cubed. For h here, again, this is going to be a product rule, because we have this function times the sine function. So I'm going to differentiate the e to the 2x first. So the derivative would be e to the 2x times the derivative of the exponent, and that's why this 2 is in front. So that's the derivative of the first function times the second, plus, and then we do the opposite. First function times the derivative of the second function. The derivative of sine is cosine, so it would be cos 4x minus 5, times the derivative of what's in here, which would be 4. And that's that 4 right there. Now the only thing I've done from this line to this line is I would normally write that 4 in front, so it's 4e to the 2x cos 4x minus 5. For I here, f of x is 6 to the power of 4x. The derivative of any exponential function is the original function times, and times the derivative of the exponent, that's where the 4 comes in. And if the power is not e, you have to multiply by the ln of the base. So it's 4 ln 6, 6 to the 4x. Didn't have to worry about that, for example, here when I was differentiating the e. You can actually do it, but the ln of e is 1, so it doesn't affect the derivative at all. It's the same thing. Last one here, j 4 cos 4x squared. So the derivative of cosine is a negative sine. So we'd have negative the sine of 4x squared times the derivative of what's here. Now, the assumption is that there's brackets around this, like this, when you see that. So, and times the derivative of the 4x squared, which is 8x. And I would normally multiply that 8x by the negative 6 here. So that's why it's negative 48x, and then sine 4x squared. So for question number 19 here, we have a transportation company that's, when they sell 2,000 bus tickets each day when they charge $10 per ticket. And they believe that every $1 they increase the ticket price, they're going to sell 100 tickets less. Increase the price, but sell less. So you're asked to use the calculus to determine what price that they should charge to maximize the revenue, to get the highest possible revenue. Now, I'm going to let X represent the number of $1 ticket increases in ticket price, and R of X is going to be the revenue as a function of however many times we increase the price. The way you calculate revenue, it's the price you're charging multiplied by how much you're going to sell. And so this is where this function comes from, R of X, the revenue, and the price starts out at 10, so we're going to add X to that. So for example, if X was 3, then we would be charging $13. So X is how much we're going to increase the price, or the number of times we're going to increase it $1. The number of tickets sold starts at 2,000, and they think that they're going to lose 100 every time they change the price $1. So we're going to take off that 100 X times, or 100X. And so I would expand this out. Now the maximum occurs where the derivative is 0. So I expand this out. So 10 times 2,000 is 20,000. 10 times negative 100x is negative 1,000x. This will give you 2,000x and negative 100x squared. Add the like terms, and that's what we have for the revenue function. So differentiate it. This is a constant, so its derivative is 0. The derivative of this would be 1,000 and then minus 200x. Now, the derivative occurs, or maximum when the derivative is, the maximum occurs when the derivative is 0. So setting the derivative to 0, we would get 200x equals 1,000, so x is 5. So if x is 5, then the price is going to be 10 plus 5, or $15 per ticket. And that should yield the highest possible revenue. Question number 20, we're asked to find the equation of the tangent line to this function where x equals 1. Now the slope of the tangent line is the derivative at that point. So we would differentiate this function. So power rule here, derivative 4x cubed would be 12x squared, derivative negative 5x squared would be negative 10x, and of course 8x's derivative would be 8. And so we put 1 in place of x, 12 times 1 squared minus 10 times 1 plus 8, which is 10. So that's the slope of the tangent line. So I'm just going to use y equals mx plus b. So 10 is the slope, that's the m, and we're told that x is 1, so we can put 1 in place of x, but we need to find what y is to know what to put in place of y. And so we can just put the 1, x equals 1, back in the original function. And so if we do that, that's what the calculation looks like, and you get 7 for y. So that's why the y value is 7. And so 7 take away 10 is negative 3, so that's the y-intercept of the line. So the equation would be y equals 10x minus 3. In question number 21, this is the first of 2 questions where you're asked to sketch a couple graphs, find all local max and mins, intercepts, any asymptotes, points of inflection, concavity, the whole 9 yards. So let's start with intercepts. So this is our function here. And so notice there's a common factor of x squared you can factor out. And so we get x squared times the x squared minus 8x plus 18. Now, if you try to factor this, you can't. There are no numbers that add to negative 8 and multiply to 18. If you try to use the quadratic formula, you find there is no solution as well. Okay, so I haven't bothered to go through all that. But if you set the x squared factor to 0, you get x equals 0. So there is an x-intercept at 0, which means the y-intercept is also 0, because they're the same. They have to be the same thing if they're 0. So 0, 0 is the one and only intercept. Now, on to the calculus part. Let's take the first derivative to find out where any extrema, local max or min points might occur. So the derivative of this function would be 4x cubed minus 24x squared plus 36x, just using power rule in each of the 3 parts. And so we set that equal to 0, and you can factor a 4x out. And so you get x squared minus 6x plus 9. That will factor as well. That's actually a perfect square trinomial. Or you could think of, well, what adds to negative 6 multiplies to 9, which is negative 3 and negative 3. So the 2 numbers are the same, so it factored into x minus 3 times x minus 3, or x minus 3 squared. And so if we set the 4x factor to 0, you get 0. So it looks like at that x and y intercept there might be an extrema point, and then at 3 as well, because 3 is what makes this one 0 as well. So there's 2 potential extrema points at 0 and at 3. So that's the first derivative. Let's talk concavity and points of inflection next. So if we differentiate this, we get 12x squared minus 48x plus 36. And so we set that equal to 0. A 12 will divide out, making this a lot smaller. And so what adds to negative 4 multiplies to 3 would be negative 3 and negative 1. Okay, so if we set x minus 3 to 0 and x minus 1 to 0, we get 3 and 1. Notice that 3 is a possible point of inflection, but it was also a possible extrema, and that generally means that it's going to be an inflection point, not a local max or min. I'll talk about that just a little more when we talk about the graph down here in a moment. To know which is which, if it's a possible point of inflection and the concavity changes, then it has to be point of inflection. And so let's plot some of these points here. Of course, we have the 0, 0 point. At 1, there's a possible point of inflection here. So let's find f of 1. Again, going back to the original function. So this guy right up here. So putting 1 in place of x, 111 is a point on the graph. If we put 3 in, that was the other place that could be a point of inflection. then 327 is another point on the graph, a possible inflection point, and that certainly looks like an inflection point right there. We'll justify that with the second derivative up here in a moment. So to check whether 0 is a local maximum, we can do that using the second derivative test. Check the concavity at that place. So in the second derivative here, the 12x squared minus 48x plus 36, we put 0 because we think that's going to be a local maximum. And so that works out to 36. So remember, if the second derivative is positive, that means the graph is concave up there. So at 0, there has to be a local minimum point. So in the graph, the 0, 0 is a local minimum point. Now, I think down here that there's possible inflection points at 1 and at 3. So that's why I'm going to talk about the 1 point for a second here. I'm going to check the second derivative. Well, I already checked it at 0, and I'm going to check it at 2 and see if concavity actually changes across the 1 point. Okay, so the 0 and 2 are examples of numbers that are below and above the 1. So at 2, if we put 2 in the second derivative, we get negative 12. So notice that concavity changed. It changed from a positive second derivative to a negative second derivative. And so that's how I know that at 1, which was the 111 point here, that's an inflection point. So at 2, I know the second derivative is negative. So, well, let's see what's happening at 3 here exactly. So at 3, the second derivative is equal to 0, and actually I really didn't need to do that because I found the second derivative was 0 here. But at 4, if I put 4 in the second derivative again, it goes back to being positive. So at 2, it's negative, and 3 it's 0, and at 4 it's positive. So at 3 it changed sign. The second derivative changed from negative to positive, so that's how I know that 3 is a point of inflection. It's not a local min or max point. So for a summary here, there's a local min at 0, 0, and the x-intercept is at the same place. There's a point of inflection at 327, and I forgot to list them here, I guess, and also at the 111 point. So there, and at 111 as well. The graph is concave down. For this part right here, between 1 and 3, it's concave down there, and then it's concave up above 3, and it's concave down below 1. So that's the first graph there. For the last question here in B, you're given the function f of x is 10 over x plus 2 squared. So to find the y-intercept, we would put 0 in place of x. So f of 0 would be 10 over 0 plus 2 squared. 2 squared is 4, so 10 divided by 4 is 2.5. So it goes through the y-axis at 2.5. Now, there are no x-intercepts because if we set the function equal to 0, there's no way it could equal 0. There's no x in the numerator here. So there's no value for x that would actually make this equal to 0. So an x-intercept of a y-intercept of 2.5, but no x-intercept at all. There's a vertical intercept at -2 because that's the value that makes the denominator undefined, or sorry, actually the denominator has a value of 0, so the function is undefined. So if we were to draw it on the graph here, it would look like that. There's the vertical asymptote. Now, because the denominator x plus 2 is squared, it doesn't matter whether you're approaching from the left side or from the right side. The denominator is always going to be positive because we're squaring it. So the graph goes up on both sides. So it will go up on this side and also up on this side as well. Now, let's see if there's any local mins or maxes. Well, we could take this function, and I'll bring the x plus 2 squared up. So that's why it's the power of -2. And differentiate this. So the -2 comes down and multiplies by the 10 to give you -20. Subtract 1 from the exponent. So that's the derivative. So we write it as -20 over x plus 2 cubed. Now, that can't equal 0 for the same reason we couldn't find an x-intercept, because the numerator is just a 20. There is no value that would make it 0, so there are no local max or mins. Second derivative, well, we could take this and differentiate. So -3 multiplied by -20 is 60, and reduce the exponent by 1. So -3 minus 1 is -4. So the second derivative is 60 over x plus 2 to the fourth. And again, that has to be always greater than 0. It could never equal 0 because, again, there's just a constant number in the numerator. So if it's always greater than 0, the entire graph is entirely concave up. So as a summary, this is what we have. There's no local min or max. I didn't write the no local max here, but that would be true as well. The y-intercept is at 0, 2.5, which is right there. There's a vertical asymptote at -2, goes up on both sides. No points of inflection, and the graph is entirely concave up. Now, it's undefined at -2, so you actually should list this as intervals, as it's concave up below -2 and also above -2. At -2, the graph doesn't exist, and so that's what it looks like. And that's the end of the review.